All right, welcome to the deep dive. This is where we distill complex information from your sources into the most important insights, giving you a comprehensive understanding without the information overload.
And today, we're embarking on a truly monumental system design journey. Our mission is to break down critical system design challenges, exploring each one in meticulous detail, ensuring absolutely no stone is left unturned.
That's the plan.
We are going to build your understanding chapter by chapter, focusing on every single detail before moving to the next.
That's right. Think of this as your personal, incredibly in-depth masterclass in foundational system design. We're going to cover everything from the core functional requirements to the deep nitty-gritty of the most advanced solutions. We're talking about the very systems that underpin so much of our digital world, and we'll analyze the motivations behind every design choice, looking at what works, what falls short, and what truly excels.
Yeah.
So let's unpack this, starting immediately with our very first challenge. Hashtag tag 1. Design a news aggregator. Okay, first up, our first major challenge today is designing a news aggregator. So imagine building something on the scale of, say, Google News, a platform that seamlessly brings together news articles from literally thousands of source publishers all over the world.
Right.
It sounds deceptively simple, maybe, but the scale and the real-time nature make it incredibly complex.
Exactly. And when we talk about the core functional requirements, we're looking at those fundamental user interactions. First and foremost, users must be able to view an aggregated feed of news articles.
The main thing.
The main thing, yeah. This feed should draw from thousands of diverse source publishers globally. Secondly, the user experience dictates that they should be able to scroll through this feed seemingly infinitely, without hitting a hard end.
Right, that infinite scroll.
Exactly. And critically, users need to be able to click through any article in their feed to visit the original publisher's website. That's key.
Now, it's important to clarify what's not in scope for our initial design of this system, meaning we're deliberately setting these aside for now.
Good point.
We're not diving into protecting user data and privacy, nor are we immediately tackling how the system should handle those massive traffic spikes during, breaking news events.
Which are crucial, but later.
Later, exactly. Monitoring and observability, while vital for any production system, are also out of our core design scope for this particular deep dive. And finally, ensuring the system is resilient against potential publisher API failures is another critical but out-of-scope consideration for now.
Yeah, we need focus.
We're focusing on the foundational aggregation and delivery mechanics first.
Building on that, the non-functional requirements are equally, maybe even more critical for a system like this. A primary consideration, and this is big, is that the system should prioritize availability over consistency. This is a direct nod to the CAP theorem, right?
Yeah.
Where in a distributed system with network partitions, you often have to choose. For a news aggregator, delivering some news, even if it's slightly stale, is generally preferable to showing no news at all.
Makes sense. Better something than nothing for news.
Precisely. Additionally, the system must be highly scalable, capable of handling a staggering 100 million daily active users, with the elasticity to spike up to 500 million daily active users during major global events.
Wow, that's a huge range.
It is. And, crucially, it needs to provide low-latency feed load times, targeting a response time of less than 200 milliseconds. That's really fast.
Yeah.
Users should see their feed almost instantly.
So, just to nail that down, 100 million DAU baseline, handling 5 times that peak, and a sub-200 millisecond feed load. That's serious scale. Let's dig into the capacity estimation for these requirements.
Okay.
When we consider the sheer volume of articles, we're looking at thousands of publishers globally. Some of these publishers might be pushing out 50 to 100 new articles per hour during peak news cycles.
Just constantly flowing in.
Constantly. Now think about feed requests. If those 100 million daily active users refresh their feed, let's say a conservative 5 to 10 times daily.
Which seems reasonable.
Yeah, that generates an astonishing 500 million to 1 billion feed requests every single day. To put that into perspective, a single highly optimized caching instance like a Redis server can typically serve around maybe 100,000 requests per second.
Which sounds like a lot, but...
But when you have maybe 10 million concurrent users actively refreshing and needing their feeds, you can immediately see we'll need to scale way, way beyond a single instance or even a handful. The numbers alone dictate a highly distributed, super efficient system.
Definitely. And to effectively manage and process this immense volume of data, we need clearly defined core entities. These are the building blocks. Our primary piece of content is the article.
Right.
This entity would encapsulate various attributes. a unique ID, the title, a summary, a thumbnail URL for that little picture, the publish date, a publisher ID to link it back, the region it's relevant to,
Okay.
and any media URLs for richer content. That's the core data. Then we have the publisher entity. This represents the source of our news. It would include its own unique ID, its name, its main website URL, the crucial feed URL, often an RSS feed or an API endpoint, and its region.
So article and publisher, the core nouns.
Exactly. These two entities form the fundamental building blocks for the whole aggregation system.
And how do users actually interact with this intricate system? Our primary API or system interface is designed to be, well, pretty straightforward for the end user, right?
Yeah, keep it simple for the client.
The main endpoint would be a GET feed request. This endpoint would accept query parameters, page for pagination, limit for the number of articles per page, and region to filter geographically.
Makes sense.
Our initial approach for this feed relies on simple offset-based pagination. And it's important to note a design decision here. We're not planning at this stage for a specific API endpoint to view a single article within our system.
Okay, so no articles.id.
No. Instead, when a user clicks an article, their browser navigates directly to the original publisher's website using the URL that's embedded within the article object itself.
Right, keeping our system focused purely on aggregation and redirection.
Exactly. Focuses the scope.
Okay, let's lay out the high-level design for our news aggregator. The architecture naturally divides into two main phases: data collection, or ingestion, and feed delivery, which is serving the content out to users.
Got it. Collect and serve.
Pretty much. For data collection, ingestion, the heart of this phase is the data collection service. This operates as a persistent background process, continuously gathering content from all those sources. It's designed to regularly pull publisher RSS feeds and APIs.
How often?
Well, the polling frequency is adaptive, typically maybe every 3 to 6 hours, but it's adjusted based on how often each specific publisher actually updates their content. Some update way more often than others. This service does several critical things. It extracts the raw article content and its metadata title, summary, date, etc. It also downloads any media files specified for thumbnails. These thumbnails then get stored in a spiralized object storage solution, like Amazon S3, which is great for scalability and durability of binary files.
Okay.
Concurrently, the extracted article data, along with references to those media URLs in S3, is saved into a central database. Our content comes from thousands of publishers worldwide, providing content via RSS feeds or dedicated APIs. And RSS, really simple syndication, is key here.
Still relevant.
Very. It's a simple XML format, standardized, lightweight to parse, making it really efficient for our collection service.
Okay, so that's collection. What about delivery?
Right. Feed delivery service. This is where users access the news. The core component is the feed service.
Yeah.
This service receives user requests, usually coming through an API gateway, which acts as the front door for all client traffic.
Oh, standard pattern.
Exactly. When the feed service gets a request, it queries the database to get articles. It filters them based on user criteria, region, page, limit. Once retrieved, it formats the response, assembling the article data, metadata, and those media URLs pointing to object storage, and returns it to the client app website.
And that infinite scrolling.
Ah, yes, infinite scrolling. Our initial simple enhancement uses offset-based pagination page and limit. But, as we hinted, this immediately runs into a big problem: pagination drift.
Explain that again.
Sure. Because new articles are constantly being published and inserted into the database, the underlying order keeps shifting. So if a user scrolls down, gets page 1, then asks for page 2, new articles might have been inserted before page 2 started. This means page 2 might repeat articles from page 1, or worse, the user might completely miss new articles that were inserted just above where they left off.
Oh, right. That would be super annoying.
Extremely. Especially with news where 50, 100 new articles can appear per hour. A user browsing for just 10 minutes could easily hit this drift multiple times. It leads to a frustrating, inconsistent experience.
Definitely need a better way.
Yeah, it immediately highlights the need for a more robust pagination strategy, which brings us perfectly to our deep dives.
Okay, that basic setup, as outlined, works for simple needs. But scaling to hundreds of millions of users, demanding that low latency, managing global distribution, it's clear this needs significant enhancements. So let's jump into those deep dives, starting right with that tricky pagination problem.
Right. Our first deep dive: how to ensure consistent pagination for infinite scrolling. As we just discussed, the main challenge with offset pagination is that pagination drift, new articles messing up the results.
Okay.
A great solution is timestamp-based cursors. Instead of page numbers, the feed service, when it returns a batch of articles, also includes a cursor. This cursor is typically the publish date timestamp of the last article in that specific response.
Like a bookmark in time.
Exactly. For the next request, the client doesn't ask for page 2. It sends a query like, where published at cursor timestamp order by published at deci limit 20. This fundamentally eliminates drift because queries are relative to a fixed point in time the last article the user saw.
Smart.
Very. But for this to be efficient, you absolutely need an index on the published at column in the database.
Makes sense. Any downsides?
Well, even this great solution has a subtle challenge. It's possible, though maybe rare, for multiple articles to have the exact same publish at timestamp, maybe down to the millisecond if they're ingested very close together.
Oh, collisions.
Right. If the cursor matches a timestamp with multiple articles, the cursor timestamp query might inadvertently skip some of those articles published at the same time, leading to an incomplete feed.
Okay, so timestamp cursors are great, but not perfect for news where timing is everything. That leads us to an even greater solution, using monotonically increasing article IDs.
Tell me more.
The idea here is to design our article IDs so they inherently increase over time. A perfect fit for this is something like a UID, a universally unique, lexicographically sortable identifier.
UALA.
They're unique globally, like UVIDs, but they're also sortable chronologically based on when they were generated. With ULAs, our query becomes incredibly robust and simple. We're articleid cursored order by articleid deci limit 20.
So you're sorting by the ID itself, which guarantees order.
Exactly. It completely eliminates the timestamp collision problem. And it's remarkably fast to execute with a simple index on articleid.
Sounds ideal. What's the catch?
The main challenge is that it requires upfront planning. You have to choose this ID strategy from the start. If you've already built your system using random UIDs, switching to ULAs means a complex, possibly painful data migration.
Right. Migrations are tough.
And the system generating these ULAs needs really high throughput. Also a key business decision. A ULA sorts by ingestion time when we got the article, not necessarily the original published time from the source. That distinction might matter for news freshness.
Got it. Makes sense. Good trade-offs to consider. Okay, second deep dive. How to achieve low latency feed requests under 200 milliseconds. The fundamental challenge with direct database queries, as we said, is scale. 500 million to a billion requests daily, querying millions of articles. The database just becomes an instant bottleneck. No way it meets 200 meters.
So caching.
Caching is the way. A good solution is a caching layer with a time to live, TTL. Think Redis. The strategy is to store pre-formatted feed data article IDs, maybe some essential metadata in Redis sorted sets, organized by region.
Yeah.
Each entry gets a TTL, say 30 minutes. After that, it expires. The feed service queries Redis first. Cache hit. Great return immediately sub 200 meters, cache miss. Then it queries the database, gets the data, populates Redis, and returns to the client. For pagination within Redis, you use commands like zrev range by score with the cursor.
That sounds much better. But what are the challenges there?
Several challenges remain. First, cache misses, even if less frequent, still hit that slow database. Second, the TTL means a freshness violation. Users might wait up to 30 minutes for new articles, which is bad for news. Third, the thundering herd problem. When a popular cache key expires, tons of requests miss simultaneously, hammering the database. Leads to performance drops and inconsistent user experience right at that moment.
Okay, so TTL caching is good, but not great for real-time news. Which brings us to the great solution. Pre-computed feeds with change data capture, CDC.
This is where it gets really sophisticated.
Yeah. The core idea is shifting the work. Instead of computing the feed when the user requests it, read time, we compute and cache feeds for each region as soon as new articles are published, write time.
Proactive caching.
Exactly. The magic is change data capture. When a new article hits our main database, CDC Tech detects this change immediately at the database log level. It then triggers an update to the relevant regional caches in Redis, completely bypassing TTLs and eliminating freshness delays.
How does that flow work exactly?
Okay, the process. 1. New article saved to the database. 2. CDC system, like Debezium, detects the change. 3. CDC sends an event to a message queue, like Kafka. 4. A dedicated feed generation service, multiple workers, consumes messages from the queue. 5. Each worker processes the new article and updates the relevant Redis caches for the article's regions.
So the Redis caches are always up to date.
Almost instantly. When a user requests their feed, the feed service just reads directly from the pre-computed Redis sorted set using zrev range Super fast, under 5 milliseconds, typically.
Full article data.
Good question. You can either store full metadata in the Redis cache itself, fastest but uses more memory, or just store IDs and retrieve the full data via a secondary cache lookup or an optimized DB query. This whole pipeline guarantees sub 200 meters response and immediate freshness.
Sounds powerful. What's the downside?
The main challenge is complexity. You're adding CDC, a message queue, worker services. It's more infrastructure, more moving parts, harder to operate, monitor, and debug. But for this scale and performance, it's the necessary trade-off.
Makes sense. Okay, third deep dive. How to handle the global distribution of publishers and users. The challenge is obvious. Sources and audience are everywhere. We need efficient collection and delivery worldwide.
How do we tackle that?
It's a multi-pronged solution. First, geographical sharding or replication. Deploy services and databases in multiple regions globally. Bring the data closer.
Right.
Second, a content delivery network, CDN, absolutely essential for static assets, especially thumbnails, caches them at edge locations near users.
Yeah.
Third, optimized data collection. Our data collection service needs smarts. Implement publisher priority. Big names like CNN, BBC get higher priority. Dedicated workers pull them more frequently, maybe every 5-10 minutes, to catch breaking news fast.
What about publishers without nice feeds?
That's where intelligent web scraping comes in as a fallback. Specialized scrapers navigate sites, find links, extract content, normalize it. We'd use fingerprinting to deduplicate. Schedule intelligently. Scrape big sites often, smaller ones less often. Combines RSS freshness with scraping coverage.
But scraping is fragile.
Yeah. Very. Challenges of scraping. High maintenance, HTML changes break them, slower, less reliable, potential legal issues. It's a strategic fallback, not the primary method.
So what's the best way to get content?
The optimal solution, webhooks. Push-based. Instead of us polling, publishers notify us immediately when they publish. They send a POST to our dedicated POST webhooks article published endpoint with the article data.
They tell us.
Exactly. This requires a robust webhook infrastructure, a high availability endpoint to handle spikes, rigorous payload validation, data extraction, queuing for processing, and strong webhook authentication, shared secrets, API keys for security.
Okay, and building on that distribution, let's talk thumbnail optimization. Basic approach. Store thumbnails in S3, reference URLs in the DB. Thumbnails load directly from S3, reducing our server load.
Standard practice.
But an improved solution combines S3 plus CloudFront CDN plus multiple sizes. During collection, when we get a thumbnail, we generate multiple variants, maybe 300 by 200 for web, other sizes too.
Responsive images.
Right. Upload all variants to S3, store their URLs. Then, CloudFront caches these thumbnails at its global edge locations. Users get the thumbnail served from the closest edge, making it load super fast, easily sub 200 meters.
What's the challenge there? Just storage cost.
Pretty much. The main challenge is slightly higher storage costs for the variants. But honestly, it's usually minimal compared to the performance gains. Plus, the CDN dramatically reduces direct S3 requests, often by over 90%, which saves bandwidth costs, so it can even be cost-effective overall.
Makes sense. Okay, next up, how to scale feed service servers and cache layers for those massive throughput numbers.
Let's start with the feed service. Challenge. Single server, no way it handles 10 million concurrent requests. Solution. Horizontal scaling with auto-scaling groups.
Standard web scaling.
Exactly. Multiple instances behind load balancers, auto-scaling provisions, new instances based on CPU memory load. Crucially, our feed service is stateless. It doesn't hold user-specific data on the server. That makes horizontal scaling really straightforward.
Good. And the cache layer. Redis.
Right. Redis. Challenge. Single Redis instance, even if powerful, gets overwhelmed by 10M users. It handles maybe 100K or exec. Solution. Redis read replicas.
How does that work?
Each regional Redis master instance, which handles writes, gets multiple read replicas. These replicas asynchronously get updates from the masters, but can serve read queries independently. This distributes the massive read load.
Then sharding isn't needed for storage.
Probably not for storage itself. Given our estimate of maybe 2,000 recent articles per region cached, a single Redis instance can easily hold that. The bottleneck is pure read throughput, so scaling read capacity via replicas is the key here, not necessarily sharding the data itself across multiple masters initially. Okay, our fifth deep dive for the news aggregator. How to handle category filtering and personalized feeds. This is about tailoring the experience. The challenge with a naive category filtering approach is that filtering directly in the main database is inefficient at scale.
Right, full scans or complex joins.
And filtering cached regional feeds in memory can also be inefficient if categories are sparse. Plus, caching results for every category region combo, result 25 categories by 10 regions equals 250 cache keys, becomes unwieldy.
So what's a good solution for category filtering?
Pre-compute category region feeds. Similar to our main feed pre-computation, we proactively cache feeds for each category region combo in Redis sorted sets. Feed.sports.us, feed.politics.uk.
Extend the CDC pipeline.
Exactly. The CDC pipeline populates these two. The filtering logic then becomes super simple. Read, say, 1,000 cached article IDs from Redis. Maybe do some tiny filtering in app memory, 1-2 meters. Memory usage is reasonable because we only store IDs, not duplicate article content.
Okay, that handles categories. What about true personalized feeds? That seems way harder.
It is. The challenge is scale. If you try dedicated caches for millions of users, 50 M users, 1,000 articles equal 50 billion cache entries, memory requirements explode. It's maybe 200, 500x larger than category caching. Plus, cache staleness is a problem if user interests change fast, and you risk missing breaking news.
So what's the optimal play for personalization?
The optimal solution is a hybrid personalization with dynamic feed assembly. Instead of caching per user, we store lightweight user preference vectors, kilobytes per user.
Compact interest profiles.
Right. Then we assemble personalized feeds on demand by dynamically mixing content from our pre-computed category feeds. We manage maybe a few hundred category caches, not millions of user caches.
How does that assembly work?
A dedicated feed assembly service does it.
No.
It takes the user's preference vector, looks at recent engagement, trending topics, editorial importance, and intelligently combines articles pulled from relevant category feeds. For example, sports, tech, for a user interested in both.
What are the challenges with that?
Main challenges: reduced personalization depth compared to a full-blown recommendation engine. And the assembly algorithms need careful tuning to balance personalization with content diversity, ensuring users don't get stuck in a filter bubble. But it's a highly scalable, cost-effective way to offer personalization. #tag2, Design Yelp. All right, let's pivot. Moving from news aggregation to local discovery. Designing Yelp. You're looking for the best coffee nearby or want to leave a review for that amazing new restaurant.
Yeah.
What's the system behind that look like?
Yeah, Yelp. Okay, the functional requirements are pretty clear, very user-centric. First, users need to be able to search for businesses. Critically, this search needs flexibility by name, location, at long, and category.
Like pizza near downtown.
Exactly. Second, users need to view businesses and, crucially, see their reviews. And third, users have to be able to leave reviews that mandatory 1 to 5 star rating, plus optional text.
And what are we intentionally leaving out? The below-the-line stuff.
Right. For this design, we're not focusing on the admin side. So admins adding, updating, or removing businesses is out of scope for now. We're all about the user search, view, and review loop.
Gotcha. So what about non-functional needs? Speed seems key for search.
Absolutely. Scale and consistency are vital, especially for search and review aggregation. While the outline wasn't super detailed on all NFRs, it clearly implies a need for low latency search, targeting under 500 milliseconds. That's critical for a good user experience given the scale. High availability and scalability are also implicitly required.
And the scale.
Yeah.
How big are we talking for capacity estimation?
We're looking at significant numbers, around 100 million daily active users, and a catalog of about 10 million businesses. That sub 500 meters search latency target for that many users and businesses really drives a lot of our design decisions.
Definitely. So what are the main data pieces, the core entities?
Pretty straightforward for this kind of app. First, the business needs name, address, location, lot long, category, things like that. Second, the review holds the rating 1 to 5, optional text, the user ID, the business ID it's for, and a timestamp. And implicitly a user entity, user ID, name, etc., linking reviews back.
Makes sense. Defining the API endpoints early helps guide the design, right?
Always. For searching businesses, the main one is GET businesses. It needs query params, query text, location, category, and crucially, a page parameter for pagination.
Why is pagination so key there?
Because search results can be huge. Returning thousands of businesses at once is slow and wasteful. Pagination limits the payload, improves responsiveness.
Okay, what else?
To view a specific business, getbusinesses.businessid takes the ID, returns the business details and its reviews, and for leaving a review, posbusinesses.businesside reviews. The payload needs the mandatory rating number and optional text.
All right, let's trace the high-level design, starting with that crucial search function.
Okay, requirement 1, user search for businesses. A naive approach. Query a traditional relational database like PostgreSQL directly?
The simple SQL approach.
Yeah. Something like select from businesses where name like percent query percent and latitude between lat1 and lat2 and longitude between long1 and long2 and category equals category.
What's wrong with that? Seems straightforward.
The challenges are huge at scale. First, full table scans, searching location with between on lat long columns, and especially name searches with leading wildcards like percent query percent are incredibly inefficient. The database has to look at almost every row.
Okay, slow.
Very slow. Second, these heavy queries impact all other reads, slowing down the whole database. For 100M users and 10M businesses, this gives unacceptable performance. Forget meeting that 500 meters target.
Right, that won't fly. So the great solution.
Use a specialized search database like Elasticsearch. It's built for this stuff.
How does it help?
Several ways. It supports geospatial indexing natively using things like geohashes, quad trees, or R trees. These are optimized for location search.
Which one would you pick?
It's a trade-off. Quad trees might be better if updates are rare and businesses cluster densely, like in NYC. Geohashes are simpler, but can have boundary issues. It depends.
Okay, what else?
Elasticsearch excels at full-text search using inverted indexes, finds names or descriptions super fast, even partial matches, and it supports standard B-tree indexes for category filtering.
So it uses the right tool for each part of the search.
Exactly. And after the initial geospatial query gives a rough set, we do second-pass filtering. Calculate the exact distance using the Haber-Seen formula optimized for spherical distances like on Earth, refines the results.
What about searching by name, like San Francisco?
Good question. Need a separate location database. Maps names, San Francisco, to geographical polygons, a list of lat-long pairs defining the area. Populate this from reliable sources, index the name.
And Elasticsearch can use polygons.
Yep. Both Postgres, with PostGIS, and Elasticsearch, GeoShapes GeoPoints, can find businesses within a polygon. There's a trade-off. Geohashes are simpler but less precise for irregular shapes. Polygons are more accurate but slightly more complex.
Okay, makes sense for search. What about viewing businesses?
Requirement 2, viewing businesses and reviews. This is mostly a read operation, so our Elasticsearch solution largely covers retrieving the business details needed.
Got it. Now, the tricky one, leaving reviews, especially updating that average rating.
Right. Requirement 3, a naive approach for average rating. Synchronous update with direct calculation, maybe a cron job. User reviews, then hours later, a job recalculates averages and updates the businesses table. Bad idea.
Why bad?
Stale data. Hours or days of delay. Users get confused, they expect immediate updates.
Okay, so faster updates. What's a better solution?
Synchronous update with num reviews. Add num reviews and average rating columns to the business table. When a review comes in, calculate the new average immediately. Old rating, old num reviews plus new rating. Old num reviews plus 1. It's cheap, synchronous, getting warmer.
But you mentioned a problem, race conditions.
Exactly. Huge problem. Let's walk through it. Business. 4.0 AVG 100 reviews. User 1 submits 5 stars, reads 4.0 100, calculates new AVG 4.009, tries to update. Concurrently, user 2 submits 3 stars, also reads 4.0 100, calculates the new AVG 3.99, tries to update. Concurrently, user 2 submits 3 stars, also reads 4.0 100, calculates their new AVG. If user 1 updates first, DD is 4.009 101 reviews. Concurrently, user 2 submits 3 stars, also reads 4.0 100, calculates their new AVG, then user 2's update commits. Using the old 100 reviews value, it overwrites user 1's change. The final state incorrectly reflects only user 2's review, or maybe neither if num reviews gets messed up. Data corruption.
Yikes. Can't have that. So, the great solution.
Synchronous update with optimistic locking. Instead of explicit locks, we use versions.
How does that work?
When updating, you first read the current state, including num reviews, which acts like a version here. Calculate the new average. Then your update statement includes a where clause, where business did.id, and num reviews, initial num reviews read.
Check if it changed.
Exactly. If num reviews changed since you read it, someone else updated, the UP date affects 0 rows. The transaction fails, and your service knows to retry. Reread, recalculate, try updating again.
When is this good?
Ideal when conflicts are rare, like Yelp reviews usually are. Simpler than distributed locks. Alternatively, databases often support atomic updates within a transaction, like update, set avgrading, num reviews, number reviews, +1 whereupon. This handles it atomically at the DB level. Both emphasize getting the consistency model right.
This brings us perfectly to our deep dives for Yelp, where we'll really unpack these critical challenges. Our first one, how to efficiently calculate and update that average rating. Problem recap, those race conditions. The solution, as detailed. Optimistic locking.
Right, checking NEM reviews or a version field before committing the update. If it changed, retry. It works well for low-right contention scenarios, like reviews on, say, high-frequency stock trades.
Is there an alternative if writes were really high?
Yeah, though probably overkill for Yelp reviews. You could buffer updates in a message queue like Kafka. Reviews go to Kafka, a worker batches updates asynchronously, trade some consistency for throughput.
But the average rating would be eventually consistent.
Exactly, which might be okay, might not. And for the database choice, a relational DB like PostgreSQL with transactions is great here. NoSQL like Cassandra DynamoDB could handle writes, but consistency becomes much harder to manage, explicitly needing CDC or complex custom logic.
Okay, second deep dive. Improving search for complex queries. Recap. Traditional DBs are bad at location name searches due to full table scans. Solution: Elasticsearch.
Right. Elasticsearch is purpose-built. It uses geospatial indexes, geohashes, quad trees, R trees. We talked about how they work encoding lat-lon dividing space, and the trade-offs like geohash boundary issues versus polygon precision. Full text search via inverted indexes maps words to businesses for lightning-fast text lookups. B-tree indexes for efficient category filtering.
On that second pass filtering.
Yeah, Haversine formula. The geospatial index gives a rough set. Haversine refines it to exact distances, crucial for accuracy.
And searching by location name, like San Francisco.
Need that separate location database mapping names to polygon geoshape data. Elasticsearch queries geoshape fields to find businesses within the polygon. This location data is static-ish, updated asynchronously, doesn't slow user requests. Simple geohash substrings don't work well for irregular city shapes.
Got it. Our third and final deep dive for Yelp.
Right.
Database considerations and scalability with that Staff Plus perspective.
Right. So write throughput for reviews, relatively tiny. A message queue isn't immediately necessary for the review write itself. Beta volume. Even 10M businesses, millions of reviews. It's manageable initially without aggressive sharding. A read replica and maybe a cache might suffice.
And the idea of avoiding new tech.
Crucial insight. For that location to polygon mapping, if write throughput is tiny and the data static, maybe use Postgres with the PostGIS extension instead of adding Elasticsearch just for that. Avoids operational complexity, consistency issues between stores.
So it's about justifying choices.
Exactly. Acknowledge complex solutions, sharding queues exist, but articulate why simpler options work for specific parts of Yelp's system, given its particular scale and access patterns. For example, low review writes versus high search reads. Choose the right tool, not always most complex one. That shows deeper understanding. Tag 3, design Strava.
All right, let's shift gears. Get active. Designing Strava next. The fitness tracking app runs, rides, leaderboards. This means tons of location data, real-time tracking, social feeds, a fascinating mix.
Absolutely. The core challenge really is handling that continuous stream of real-time activity data from mobile devices, then processing it for immediate display like your current pace and map, and for long-term aggregation for leaderboards and stats.
And the non-functional needs.
Implicitly, high availability is crucial. Users need to be able to record their runs reliably, and scalability to handle potentially millions tracking simultaneously. Low latency for updates is also implied.
What kind of numbers are we talking about? The capacity estimation.
Potentially 10 million concurrent activities. That's 10 million people tracking at once. Each sends GPS coordinates frequently, say every 2 to 5 seconds.
Wow.
If you have 100 MN daily users, maybe averaging 600 updates per day, like a 30-min run updating every 3 secs, that translates to 60,000 updates per second, and that's without peak load. This immediately tells us we need a highly write-optimized database.
Makes sense. What are the core entities to track all this?
Primary one is activity, includes type, run ride, state, started, pause, complete, start to end time, duration, distance, the actual route, a sequence of GPS points, and the user ID. Implicitly, a user entity, user ID name. And for the social side, a friend entity representing the follow relationship, uni or bidirectional.
Okay. And the API to manage this?
Needs to cover the life cycle, create activity, post activities, payload specifies type, run ride, update activity state, patch activities.activity ID, using patch for partial updates like state paused or state complete is more efficient.
Right, just send the change.
Exactly. Get list of activities. Get activities.mode user friend size. Returns a subset of fields for efficiency in lists. Get activity by ID. Get T activities.activityID returns the full details, including the map row.
All right, let's sketch the high-level design. Start simple, layer on complexity.
Okay, first requirement. Create, update, and complete activities. Starts on the client side, the app. records GPS coordinates every 2 to 5 seconds using device location services. Start activity. Client sends post activities. Server stores initial metadata, user ID, type, start time in a database, maybe PostgreSQL initially. Pause resume. Client sends patchactivities.activityID with state updates. Complete. Client sends patchactivities.activityID with state complete.
How do you handle pause time accurately?
Good point. Don't just do current time, start time. Track active duration by summing intervals when the state was started, pausing the calculation when state is paused.
Got it. Second requirement, view activity data, route, distance, time, during activity.
During the activity, the client continuously records GPS. It calculates distance locally using the Haversine formula on the coordinates. This data is displayed right on the client's screen.
Third requirement, view completed activities, own and friends.
For a list view.client, getTactivities.mode, user friends for basic info paginated. For detail view.user clicks, client getTactivities.activityID for full details. For the map display, the route, array of coordinates, is passed to mapping APIs like Google Maps to show the path.
So that covers the basics. But the real world intrudes, right? Running with no signal, seeing friends' live progress, these need deeper exploration. Let's hit the deep dives.
First one, how to support tracking activities while offline. This is super common for mobile apps. The key insight: if real-time sharing isn't needed right now, data can be recorded locally and synced later.
How does that work?
The approach. 1. Use on-device location services to record GPS coordinates continuously. 2. Store this event data locally, maybe in an in-memory buffer first, like an array of points timestamps. 3. Periodically persist this buffer to local storage, for example every 10 secs, to prevent data loss if the app crashes. Use core data user defaults on iOS, shared preferences SQLite on Android. 4. When the activity completes or the user gets back online, sync the locally stored data to the server.
What's the benefit?
It offloads significant write load to the client. Simplifies the backend ingestion, especially for the basic tracking.
Yeah.
The backend still needs to scale to process the sync data, but maybe not for extreme real-time per second ingestion across the board.
But you have to trust the client.
Mostly, yes. The client is the source of truth here, but the server can still do sanity checks on the uploaded data, like flagging a run that claims a 2-minute mile.
Okay. Second deep dive. How to support real-time sharing with friends. If I want to see my friends run live on a map.
Right. For this, we need to reintroduce server updates. During the activity, the client must periodically send location updates every 2 to 5 secs to the server. The server persists these and broadcasts them to friends.
So, how to broadcast. Polling versus WebSockets SSE.
This is interesting. The source argues polling might be simpler and effective here. Why? Updates are predictable every 2 to 5 secs, allowing efficient polling intervals. Lower overhead than maintaining tons of persistent WebSocket SSE connections.
But polling has latency.
It does, and it's inefficient if polling when nothing changed. WebSockets offer true real-time push-based updates, implement with a real-time tracking service, PubSub for broadcasts, immediate updates.
What's the downside of WebSockets then?
Complexity, huge jump. Stateful connections, connection management, sticky sessions for load balancers, routing, handling disconnects, reconnects. The source argues that for this specific predictable update pattern, optimized polling might be a pragmatic starting point, avoiding the heavy lift of WebSockets E unless absolutely necessary. It's a trade-off. Okay, third deep dive. How to efficiently update and display leaderboards. The competitive parts.
The naive way.
Naive approach, aggregation query. Select u.name, suma.distance, GRUP by u, .user order by total distance DASC. Bad idea.
Why that?
Very slow. Aggregating millions of activities on every request, kills the database, performance tanks, not real time.
Okay, so what's better?
Better solution. Periodic aggregation. Have a separate leaderboard table with pre-calculated totals. A background job, cron, runs daily, hourly to update aggregates. Leaderboard query becomes a simple select from this table.
Downside.
Eventual consistency. Leaderboard isn't real-time, it's as fresh as the last cron run. Need to balance update frequency versus DB load.
Which brings us to the great solution.
Redis sorted sets, ZS sets. Ideal for leaderboards.
How?
Use Redis Z-sets. User IDs are members, total distances are scores. Redis keeps them sorted automatically. When a new activity finishes, just increment the user's score using ZNCRBY. Querying the top N, use zero of range. Extremely fast, O log N or O1, effectively for small n, real-time and scalable.
What about filters, like leaderboard for the US only, or for this week?
Good question. Country filter. Maintains separate Z-sets per country, for e.g. leaderboard.run.us. Update the right one when an activity is logged. Time range filter, more complex. Combine Redis z-sets and hashes. One ZS set activity ID is member, timestamp is score, lets you query by time. Redis hashes, activity ID is key, storing user ID and distance. To query, get activity IDs from the z-set using ranked by score for the time range. Then, fetch user ID and distance for each ID from the hashes. Finally, aggregate distances by user ID and memory.
Challenges with the Redis approach.
Data consistency between Redis and the primary DB is key. Need robust failure tree logic for Redis updates. Also, Redis memory limits if you try to store every possible filter combination. Mitigation cache, frequently access leaderboards, calculate less common ones on demand. Okay, fourth deep dive for Strava, scaling to support 10 million concurrent activities, that massive continuous data stream.
Where do we start? The database.
Yes, the database. Persistence layer. Storage itself is significant. 10M activities, 600 points activity size equals lots of data. The bigger issue is write throughput, 60K update TSEC. Traditional RDBMS, Postgres MySQL struggle above 5K write sec.
So no cool.
A write-optimized NoSQL like Cassandra could work. However, the design mentions potentially writing live activity data to Redis, hot data, then flushing to a slower persistent DB, Postgres or NoSQL, in batches after the activity. This reduces the direct DB write load significantly. Essential. Shard by userid, good for getting user history. Or activity, maybe with timestamp as sort key for DynamoDB. Sharding by completion time for recent activities or userid for user lookups. Plus, replication. Read replicas for handling high read throughput, viewing old activities.
What about the application services?
Stateless services can be horizontally scaled easily with load balancers, standard practice.
And the data volume long term.
Huge. 10 years of data, petabytes, requires data retention and archiving. Move old, cold activity data to cheaper storage like S3 Glacier, #Tag4. Design online auction.
All right, from tracking runs to the thrill of the bid. Next up. Designing an online auction system. Think eBay. Users list items, place bids, highest bidder wins. This was all about real-time concurrency and absolute integrity.
Yeah, this is a classic and particularly challenging. You've got the real-time nature of bidding needing super low latency. You need strong consistency for who has the highest bid and who wins money is involved. And you have to manage concurrent access, potentially thousands trying to bid on the same item at the last second.
So the non-functionals are key.
Absolutely. Highly available, bids must get through, and scalable to support, say, 10 million concurrent auctions. That's 10 million active auctions happening at the same time, each potentially getting bids.
Wow, 10 million concurrent auctions. Okay, capacity estimation. If we guess, maybe, 100 bids per auction on average.
Seems plausible for a mix of popular and unpopular items.
Okay, 10M auctions, 100 bids. That implies 1 billion bids per day. Break that down. 1 billion 100,000 seconds day. That's 10,000 bits per second sustained rate.
That's a serious write load.
Definitely. What about storage? Auction, 1 KB, bid 500 bytes, 10 EMA options, 52 weeks year, 1 KB plus 0.5 KB 100 bids, crunching numbers, about 25 TB per year.
Manageable storage-wise for modern SSDs, yeah.
But the bottleneck is clearly that database write throughput for 10K bidsec.
Agreed. Okay, core entities. We need an auction. Holds the item, start end date, starting price, current highest bid, highest bidder ID. An item. Just name description, image URL, a bid, stores amount, user placing it, auction ID, timestamp, status, accepted, rejected, pending, and implicitly a user ID, name.
And the APIs to drive it.
Simple on the surface. Create auction. PSD auctions, payload has item details, dates, price, returns the auction and item, place bid, PSD auctions.auction id bids, payload has bid details, returns the bid, view auction get t auctions.option id, returns auction and item, crucially including the current highest bid.
All right, let's walk through the high-level design, focusing hard on bidding.
Okay. First requirement. Post an item for auction, pretty standard flow. Client POS to auctions, API gateway auction service.
What does the auction service do?
Validates the request, stores the auction and item data in the database. Quick note on images. Store them in blob storage, S3, reference the URL in the items table. Standard stuff, intentionally out of scope for deep detail here.
Okay, now the main event. Bid on an item. Bids accepted only if higher. Yeah. This is the core challenge.
Right. We introduce a dedicated bidding service. Its jobs: validate bids, is it higher? Update the auction's highest bid, store bid history, notify people.
What's the naive way to update the highest bid?
Naive approach. Direct DB update with lock. Read max bid, validate, update max bid, commit. Bad idea.
What bad?
Locking rows or tables for potentially long durations during bid processing kills concurrency. Hot auctions would grind to a halt. Terrible performance.
Okay, so faster reads, cache it, better approach, cache max bid in Redis.
Getting warmer. Store the max bid in Redis for O1, reads writes, flow, client, API, gateway bidding service, Redis, re-update, max bid, max BB, store bid history, seems faster.
Sure.
Challenges, big ones. Consistency between Redis cache and the persistent DB. What if Redis update works but DB write fails? Or vice versa. State becomes inconsistent. Trying to do distributed transactions between Redis and a DB to make updates atomic is really complex and often not well supported.
Okay. So the great solution.
Use the database as the cache itself, combined with optimistic concurrency control, OCC, or pessimistic locking. Store the max bid directly in the auction table.
How does OCC work here again?
Flow, optimistic locking. 1, read max bid and a version, or numbids, from the auction table. 2, validate the new bid. 3, attempt update auction, where version of initial version read. 4, if version matches, update succeeds. If not, conflict, retry the whole process, reread, revalidate. 5, write the bid-to-bid history table. 6, commit the transaction. And pessimistic locking.
Flow, pessimistic locking, select for update.
Yeah.
1, lock the specific auction row, select for update. 2, read max bid. 3, write bid to history table. 4, update max bid in auction table. 5, commit transaction, releases lock.
Benefits.
Only locks a single row briefly, pessimistic, or uses non-blocking checks, optimistic. OCC is great if conflicts are rare.
Yeah.
Pessimistic row level is also very viable here. Keeps the DB as the single source of truth.
Okay. And requirement 3, view an auction, including highest bid.
2 needs here. See the item details, read only, less critical for real-time, and see the current max bid to decide whether to bid needs real-time consistency. Initial approach may be polling, but we'll save the deep dive for later. All right, core sketch is down, but the critical parts, ensuring bids never get lost, handling massive traffic spikes, showing the highest bid instantly. That's real engineering. Let's hit the deep dives. Our first one for auctions, how to handle high concurrent bid volume and ensure bid durability.
Yeah.
That 10K bidsec challenge, direct DB writes during surges, risky.
Yeah, direct writes can overload the bidding service, or DB drop bids, cause crashes, unacceptable. The great solution, use a message queue, specifically something high throughput and fault tolerant like Kafka.
What Kafka?
Several reasons. It acts as a huge buffer, absorbing bid surges without killing backend services. Think of it as an infinitely large waiting room.
Okay, buffering. What else?
Guaranteed ordering within a partition. Critical for auction fairness. First bid wins ties. Fault tolerance. Bids persist in Kafka even if the binding service dies, ensuring at least once processing. High throughput. Kafka handles millions of messages a sec, easily meeting 10K bids sec. Durability. Persists messages to disk, replicates them.
How do you ensure order for a specific auction?
Partitioning by auctioned. Hash the auctioned to pick a partition. Hash not percent. All bids for AuctionX always go to the same partition, processed in order. Different auctions process in parallel across partitions. Important. Not one partition per auction, many auctions share a partition.
So the flow changes.
Yep. Client bids API gateway producer lightweight service. Kafka acknowledges write. Then bid service consumer reads from Kafka, validates writes to database. If bid service fails, bid stays safe in Kafka.
Trade-offs.
Adds maybe 10 meters latency normally, but worth it for durability. The producer service can be simple and scaled easily. A single really hot auction could bottleneck its partition, but usually high KPS is spread across many auctions.
Okay, durability handled. Second deep dive. Ensure the system displays the current highest bid in real time. Polling is out. Too slow, inefficient, thundering herd.
Right. A good solution, better than simple polling, is long polling. Client requests, server holds connection open until new bid or timeout. Server maps pending request per auction, new bid, respond to waiting requests.
Challenges with long polling.
Server holds many open connections, resource heavy. Still vulnerable to thundering herd on reconnect after update. Better, but limited.
So the great solution for real time.
Server send events, SSE, or WebSockets, persistent channels. SSE is server to client push. WebSockets are bidirectional. Both give true real-time, much more efficient than polling.
How does the flow work?
Bid service, after processing bid, publishes the new max bid to a PubSub system, Redis PubSub, or maybe Kafka again. A real-time notification service, or the bid service itself, subscribes to these PubSub channels, one per auction.
And the client?
Client establishes SSE WebSocket connection to this notification service when viewing an auction. The service receives updates from PubSub and broadcasts them to all connected clients watching that auction.
What about consistency versus real-time view?
Good point. We need strong consistency for placing winning bids, handled by DB transaction. For viewing the max bid, eventual consistency is often okay. User sees their outbid eventually, even if it takes milliseconds.
How do you scale millions of SSE WebSocket connections?
Horizontally scale the notification service. Use a consistent hashing load balancer, hash on user or auction night, to distribute connections and maintain sticky sessions if needed. PubSub itself scales well. Multiple notification service instances can subscribe and push to their clients. SSE handles reconnects automatically. Okay, third deep dive for auctions. Database scalability, specifically for that write throughput. 10,000 bidsec is tough.
Main solution.
Sharding. Shard the auction table, holding max bid, and the bid history table. Common strategy. Shard by auctioned. Ensures all data for one auction is on the same shard, helping consistency within that auction.
Database choice.
PostgreSQL can work, but need careful scaling. High-throughput NoSQL like Cassandra is an option, but makes ACD tricky. The source did call row locking on auction in a relational DB a great solution, implying RDBMS is viable and preferred for consistency. Need read replicas for viewing auctions.
What about ending auctions?
Simple fixed end times. Cron job checks. Okay, but cron can be delayed, full table scans are expensive, queue with visibility timeout like SQS, problem. SQS delay limit 15 minutes is too short for long auctions, needs complex requeuing, so better options.
A workflow engine like Temporal.io or Airflow is more robust. Manages long-running processes, handles complex endings like extending on late bids, demonstrating awareness of distributed ending challenges, clock drift, concurrent termination, shows staff plus thinking. Hashtag tag 10.5. Design Instagram.
All right, let's switch gears completely from auctions to visual storytelling, designing Instagram, sharing photos, videos, following friends, scrolling through feeds. This one's all about handling massive media, fan out for feeds, and low latency. Yeah, Instagram. The functional requirements at their core are pretty simple on the surface. Users need to create posts, photos, videos, plus caption. Users need to follow other users, unidirectional. And critically, users need to see a chronological feed of posts from users they follow.
And what's below the line? What are we not designing right now?
We're intentionally skipping likes and comments, search users, hashtags, locations, stories, ephemeral content, and going live, video streaming. Focus is purely on post, follow, and the chronological feed.
Got it. Key challenges.
3 big ones: handling large media files, petabytes, generating feeds at massive scale for hundreds of millions, and ensuring low latency, 500 meters, for feed delivery. That latency target is explicit.
Okay, capacity estimation. 500 million daily active users, DAU. Refreshing feeds maybe 5 times daily. That's 2.5 billion feed generations per day.
Whoa.
Peak usage. Could be 150,000 plus feed requests per second. Traditional DB queries for feeds. Absolutely impossible.
No way.
Now, media uploads. Guess maybe 100 dev uploads day. Average size 2 MB. That's 200 terabytes of new binary data daily. Over 10 years. 750 petabytes. S3 can handle it, but cost matters. Need to archive old stuff to Glacier.
And metadata.
100 M uploads 1 KB metadata each equal 100 gigabytes of new metadata daily. Again, need to archive old metadata from expensive databases like DynamoDB to cheaper S3 eventually.
Right. So the core entities.
Simple ones. Username, post-ID user, immediate URLs, caption, timestamp, media upload status, pending complete. Follower did. Follow EAD represents the A follows B relationship.
Makes sense. API endpoints.
Create post, metadata only initially. PowerSD posts, takes maybe the caption, returns posted. The actual media upload is separate using a pre-signed URL. Follow user, paywest follows, payload has follower on follow-id, get feed, see feed.cursor. Use a cursor for pagination, infinite scroll.
Okay, let's trace the high-level design. Start with posting, then following, then the big one, feed generation.
Requirement 1, create posts, flow, client pass API gateway post service.
What does post service do first?
Receives caption, stores initial post metadata, posted caption, media upload status pending, in a scalable DB like DynamoDB, returns posted to client.
Then the media.
Uses the media upload, pre-signed URL pattern. Super important for scale and security. 1, client requests pre-signed URL from post service. 2, post service generates a temporary time-limited URL for direct upload to object storage S3. 3, client uploads media bytes directly to S3 using that URL, maybe chunked multiparter. 4, after upload, client sends pat.ch to post service to update post metadata. S3 object key media upload status complete, though server-driven updates via S3 events are more reliable.
Got it. Requirement 2, follow users.
Simpler. Client API gateway day full service, follow service receives POC follows, inserts a row, follower-id, follow-id, into followers table. DynamoDB likely.
Index is needed there.
Crucial. Need index on follower ID partition key and followed sort key for who I follow, and a global secondary index GSI on follow ID as partition key for the reverse, who follows me.
Makes sense. Now, the main challenge, chronological feed generation. What's the naive approach? Fan out on read.
Yep. Flow. Client GATT feed, API, gateway, post service. Post service then. 1. Queries followers table for followed users. 2. For each followed user, queries post table for the recent posts. 3. Combines all retrieved posts, sorts chronologically. 4. Returns paginated results.
And the challenges. We know this is bad at scale.
Massive challenges. Slow. For users following thousands. Requires 1,000+ queries to post table. Unworkable. Read amplification. 500 meter DAU refreshing feeds equal billions of dB reads. Unsustainable, expensive, violates the 500 meters latency target easily.
Yeah, that approach just melts databases. Okay, this leads perfectly into the deep dives for Instagram, how they actually handle feeds and media at this insane scale.
First deep dive, how to achieve low latency feed generation.
Yeah.
500 beacons at scale. Recap. Fan out on read is dead due to read amplification slowness.
So a good solution, simple caching. Add Redis, cache individual posts.
It helps a bit, but doesn't solve the core problem. Cache needs to be huge. Still performs the expensive fan-out reads, treats the symptom, not the disease.
Right, so the great solution, pre-computed feeds. Fan out on write.
Explain that again.
Shift the work. Generate the feed when a user posts write time, not when a user requests read time.
How do you store these pre-computed feeds?
Feed storage. Use Redis sorted sets, ZSCT, key.feed.usery.members.posted.timestamp for chrono order. When user requests feed, read hop-in post from their zset in Redis. Single, super fast operation.
But the zset just has IDs. How do you get the full post? Post-migration option.
Good question. Options. 1. Store full post in zset. Simplest but high Redis memory usage. 2. Batch GD from post table. Get IDs from Redis, then batch GT from a DB post cache. Fewer DB calls than fan out on read. 3. Store in a separate post cache. Common balance. Store full posts in another cache. Redis KV store. 2 lookups. Feed zset, then post cache, but manages memory better.
Okay, walk through the process for fan out on write.
User posts, post service dash DB, store metadata. Post service puts posted, then user aid, onto a message queue. Kafka's QS for reliability. Based fan out service, worker consumes message.
What does the fan out service do?
Queries followers table, needs efficient index on followeed to get all followers. For each follower, adds the new posted to their Redis zset feed. Feed.followeruser. But what about celebrities? Users with millions of followers. That's millions of Redis writes per post. The celebrity problem.
Exactly. That's massive write amplification. The solution, a hybrid approach. Define a follower threshold, even 100K. Regular users, threshold. Use fan out on write. Push posts to their followers' feeds, celebrities threshold. Use fan out on read for their posts only. When followers refresh, the feed service fetches from their normal feed and explicitly pulls recent posts from any celebrities they follow, merging them in.
Clever trade-offs.
Need to tune the threshold carefully. Too low, too much fan out on read. Too high, too much fan out on write for popular non-celebs. But overall, this hybrid approach dramatically reduces read amplification, making feeds fast.
And Redis durability, critical if feeds live there.
Absolutely. Need Redis Sentinel, failover, Redis cluster, sharding, and persistence, AOFRDB snapshots to avoid data loss. Essential.
What about post updates, like changing a caption?
Simplest. Invalidate client-side CDN caches for that specific post. Next feed request refetches the updated metadata. Okay, second deep dive, how to handle large media files, photos, videos, petabytes of data.
Challenge, storing and serving it efficiently globally. The pattern, handling large blobs. Key parts. 1. Direct upload to blob storage, S3, via pre-signed URLs. Client uploads directly to S3, bypasses our servers, reduces load massively. 2. Chunk to multi-part uploads. For reliability, resuming large uploads, S3 reassembles. 3. Metadata update. Server-driven S3 event triggers Lambda job, is more reliable than client notification for marking upload complete. How do you serve it fast globally?
Global CDN distribution, CloudFront. Caches media at edge locations near users. Reduces latency dramatically. Basic CDN serves same file to everyone, though.
So the best way.
Dynamic media optimization. When media uploaded, a media processing service, internal or third-party like Cloudinary, generates multiple variants, different resolutions, formats, WebP, quality levels for adaptive video streaming. CDN serves the optimized variant based on device network.
Benefits.
Optimal user experience everywhere. Reduced bandwidth costs. It's the gold standard. Okay, third deep dive. Scalability of database and services.
Post-table partitioning. Partitioning by user rate is common, but risks hot partitions for prolific posters. Maybe wide column DB, user post table helps. Load balancers. Implicitly needed for all stateless services. Post, follow, feed, fan out. For horizontal scaling.
Database scaling, like with DynamoDB.
Global secondary indexes, GSIs, are key. Need them for different access patterns, e.g. query posts by user rate if post dog is primary key. Observability. Though out of scope, vital in real world. Monitoring, logging, tracing. Tag 6. Design Robinhood.
All right, let's switch gears again from visual feeds to the pulse of financial markets. Designing a simplified Robinhood. Stock trading platform. Focus. Live stock prices, managing buy-sell orders. High stakes here with money involved.
Definitely high stakes. Before we jump in, let's nail down some background financial terms quickly. Symbol, ticker. The abbreviation, like Meta, AAPL. Order, instruction to buy-sell. Two main types. Market order, buy sell now at the current market price. Specify shares only. Limit order, buy sell at a specific price or better. Specify shares and price. Might sit waiting.
And Robinhood's role. We're not the stock exchange itself, right?
Exactly. We're a brokerage. We interface with an external exchange that actually handles matching orders. We are not building an exchange. We assume the exchange provides data feeds, accepts orders, sends updates back.
Got it. So functional requirements.
Core ones. 1. Users see live prices of stocks. 2. Users can manage orders, create, cancel, view status.
And below the line, out of scope.
General stuff. Full observability, deep security data protection beyond payment specifics, CI/CD pipelines, focuses on price delivery and order lifecycle.
Oh, okay. Core challenge.
Handling those real-time, high-volume price updates for thousands of symbols, and ensuring integrity and visibility of financial orders. Low latency is absolutely paramount everywhere.
Indeed.
Implied NFRs, high availability, strong consistency for orders, fault tolerance. Can't lose money or orders.
What about capacity estimation? Throughput.
Thousands of symbols, 10,000 plus states. Price updates can be super frequent for volatile stocks, multiple times a second. Order volume can spike massively, market open close. Big news implies potentially thousands of orders per second needed.
Okay. Core entities.
Symbol.name, AAPL, current price. Order.position, buy, sell, dissell, symbol, shares, type, market limit, optional limit price, order, user, it is at status. Implicitly user, user ID, name.
API endpoints.
Get symbol price, DTT, symbol.name, return symbol object with price. Create order, POST order, payload has position, symbol, shares, type, optional limit price. Cancel order, delete, order.order, get order status, get order.order.
Okay, let's walk the high-level design. Start with live prices.
Requirement 1, users see live prices.
Client polling exchange directly. App polls the NYSE and NASDAQ queue. Bad idea.
Why bad?
Creates tons of connections to exchange. They won't like that. Slow price propagation, limited by poll interval. Inefficient. Polls, even if price didn't change.
Okay, better approach. Symbol price processor plus client polling us.
Getting warmer. Introduce a back-end symbol price processor service. It subscribes to the exchange's feed, WebSocket dedicated feed, gets updates, records prices. The client app then pulls our service.
Still polling, though. Challenges.
Yep. Clients still pull indiscriminately, wasted traffic. Still slow propagation from us to the client due to their polling interval. Not true real-time. Unacceptable for trading.
So the great solution for prices.
Server-sent events, SSE. Push-based, real-time.
How does that work?
Architecture. One symbol price processor gets updates from exchange, pushes them to Redis pub sub channels, one per symbol, example, price.aapl. One symbol price processor gets updates from exchange, pushes them to Redis pub sub channels, one per symbol, example, price. 2, our symbol service instances subscribe to Redis channels for symbols their connected users want. 1, symbol price processor gets updates from exchange, pushes them to Redis pub sub channels, one per symbol, e.g. price. 3, client establishes SSE connection with symbol service. 1, symbol price processor gets updates from exchange, pushes them to Redis pub sub channels, one per symbol, e.g. price. 4, symbol service receives update from Redis, pushes it down the SSE connection to relevant clients. Benefits.
Real-time updates, low latency, no wasted HTTP traffic, efficient push.
Challenges.
Maintaining persistent connections, SSE load balancer needs sticky sessions or consistent hashing. Handling disconnects, reconnects, routing connections to write symbol data. Redis pub sub is at most once, but for prices, missing one update if the next comes instantly is usually okay. Okay, prices handled. Now, requirement 2, manage orders, create, cancel, view status.
Right. Naive approach. Direct order submission to exchange from client. Bad idea.
Right.
Exchange overloading. No internal record keeping. If it fails, we have no idea what happened. Disaster for finance.
Okay. Better great solution. Order service plus queue plus order dispatch service. Decoupled and reliable.
Dive me through it.
One order service accepts PST order. First, stores order in orders database. PostgreSQL needs ACID for balance stocks with pending status. This is our source of truth. Then enqueues order details, ordered user, etc., to a message queue, Kafka's QS. 2, message queue acts as a buffer. Decouples order service from Exchange latency failures. Ensures at least once delivery. Volume drives scaling of dispatch service. Adds maybe 100 meters latency, but worth it for reliability. 3, order dispatch service. Consumes from queue, sends order to the external exchange, handles exchange protocols, off, rate limits.
Benefit.
Decoupling. Order service isn't blocked. Reliability. Queue ensures orders aren't lost, handles retries. Elastic scaling. Services scale independently. Avoids excess exchange connections. Only dispatch service talks to exchange. Okay, initial setup, clear. But the tricky parts. How do our internal systems know what really happened on the exchange? How do we maintain consistency with all this async stuff? Let's hit the deep dives.
First deep dive. How to scale live price updates. Recap. SSE plus Redis PubSub is the way. How to scale the symbol service itself.
Horizontally scale symbol service instances. Use consistent hashing on user or client side at the load balancer for sticky sessions. Each instance subscribes to Redis for symbols its users need.
What if one server gets too many symbols?
Load balancer could try routing users to servers already subscribed or use consistent hashing on symbol-i to distribute symbols across instances. Also, address Redis PubSubs at most once. Acceptable for prices, but for critical data, maybe use Kafka for the price feed too for catch-up capability. And consider batching orders to the exchange if possible.
Okay. Second deep dive. How does the system track order updates, fills, completions from the exchange? The challenge. Our orders DB is likely sharded by userid. The exchange update uses external ordered. How do we find the right record efficiently?
Solution. Use an external order metadata DB, a fast key value store, RocksDB or a GSI in NoSQL, or secondary index in RDBMS. It maps external ordered user.
When is this mapping created?
By the order service, synchronously, right after submitting to the exchange and getting back the external ordered, ensures the map exists before updates arrive. So the trade processor flow, handling exchange updates. 1, receives update webhook feed with external ordered. 2, queries external order metadata DB using external ordered to get ordered user quick lookup. 3, uses userid for sharding in order to efficiently find and update the record in the main orders database.
Is there a simpler way?
Yes, an alternative. If the Exchange API allows a metadata field, we pass our internal userid, ordered in that field when submitting. The Exchange returns it in webhooks. We just parse it. Common pattern, avoids the extra DB.
Security point.
Right. Passing internal IDs. Consider security privacy. Maybe use separate external ordered columns, or encryption tokenization. Okay. Third deep dive. How does the system manage order consistency and fault tolerance? Meaning, our internal state matches the exchange state, even with failures. The problem. What if we send an order, exchange accepts it, but we crash before updating our DB? We lose track of an active order.
The solution uses write-ahead log event sourcing principles implicitly in our flow. Order service stores order in orders DB with pending status before sending to the message queue. DB is source of truth. If DB write fails, stop. If DB write succeeds but queue write fails, retry queue write, at least once delivery helps. Idempotency, critical. Client sends client order idempotency token. POC order checks this key. If exists, return existing order status, don't create duplicate. Prevents double orders on client retry. What about handling exchange failures on responsive orders? Exchange down, limit order never fills.
Need asynchronous processing of exchange responses. Trade processor updates DB with confirmed statuses. For unconfirmed orders, a background reconciliation service periodically queries the exchange or uses end-of-day reports to reconcile our state with theirs.
ACID property.
Absolutely essential for the orders DB. Ensures stock quantities, cash balances are consistent, especially with concurrent ops.
And replication strategy for orders DB.
Synchronous replication. Guarantees strong consistency and durability for critical financial data. Write confirmed only after primary plus replica commit. Contrasts with price feeds, eventual consistency, okay? Any additional deep dives a top candidate might bring up.
Yeah, proactively mentioning things like excess price updates, how to avoid overwhelming client if stocks trade super fast, client throttling, rate limiting, sending deltas, limiting exchange correspondence, more advanced batching strategies. Security. Using elastic IPs for whitelisting with Exchange, strong API key digital signature authentication. Shows broader thinking. Security. #TechTech7. Design Google Docs.
All right, shifting from finance to creative collaboration, designing Google Docs. Browser-based, real-time, multi-user document editing. Seeing cursors move, changes appear instantly. Synchronization and consistency are the name of the game here.
Absolutely. The core challenge is exactly that, achieving real-time synchronization and consistency of the document state across many clients, especially when they're making potentially conflicting edits concurrently. Implied non-functionals are key. High availability, scalability, maybe thousands editing one doc concurrently, but not millions on one doc. Low latency for edits, and absolute consistency. Everyone must end up seeing the same correct document.
What are the key data pieces, the core entities?
We need the document itself, the rich text content. Critically, the operation or edit represents a change, like insert A at 5 or delete from 10 to 13, not the whole doc, just the delta. Then the user, collaborator, and cursor presence, the ephemeral data showing where users are and if they're online.
Okay, let's think about the high-level design. First, understand the core problem, concurrent edits.
All right, simple example. Doc is hello. User A adds hello world, intends hello world, edit EA, insert hello world at post 5. User B deletes, edit intends hello, edit deletes one shot at post 5. User B deletes hello, edit ebb. If they arrive concurrently at a naive server, the final state depends on arrival order. Maybe hello world, maybe hello world. Edits get lost or mangled.
So the solution?
The classic solution used by Google Docs is operational transformation, OT.
How does OT work?
It relies on a central server to establish a definitive order of operations. When a client sends an edit, it's not just applied blindly, it's transformed against any concurrent edits that the server has already applied since this client's edit was generated.
That's form.
Yeah. If user A's edit EA hits the server first, it's applied. When user B's edit E arrives later, the server transforms EB relative to EA adjusting F's delete position because EA inserted text. Then the transformed EB is applied. The magic is both users eventually converge to the exact same final state, regardless of local timing.
And OT sends operations, not the whole doc.
Crucially, yes. Only sends the small operations, deltas. Edit one char and one EB doc. Send the one char change, not one EB. Key for efficiency. Google Docs likely uses OT because it's memory efficient, good for text, and fits their centralized server model.
Is there an alternative? CRDTs.
Yes, conflict-free replicated data types. Different approach. Make every edit commutative, apply them in any order, always get the same result. Often involves giving every character a unique, ordered position number, like 4.6.
Benefits of CRDTs.
Nodes can be independent, good for more collaborators, P2P systems, offline work.
Drawbacks.
Generally more complex than OT for rich text. Simpler CRDTs exist. Counters, sets. But text is hard. Google likely preferred OT for its strengths with text and central server fit. CRDTs might be better for massive scale, or P2P, like WebRTC apps, Figma.
Okay, so the core OT architecture.
Client, browser, sends edits, receives updates via WebSockets, API, gateway routes requests, document service, centralized for OT. This service receives edits, applies OT logic to ensure consistency, stores document operations in a document operations DB, maybe Cassandra, sends transformed updates back to other connected clients for that doc. Also need a document metadata DB, stores the doc version IDs, etc., and real-time cursors presence.
That's ephemeral data handled by the document service. Since all users on a doc connect to the same document server required by OT, it can directly push cursor presence updates to connected clients. Okay, so we have a working editor, maybe scales to a few thousand users per doc. But how do we scale to millions of total connections? Manage history, compact logs, let's hit the deep dives.
First deep dive, how to scale to millions of WebSocket connections. Challenge, single document service is a bottleneck and single point of failure. Multiple layers. First, terminate WebSockets at the edge, API Gateway Edge Service. Handle the stateful WS connections early. Expose a simpler, maybe stateless, internal API to backend services. Keeps document service focused on OT.
How to scale the document service itself.
Deploy multiple document servers. Use consistent hashing. Client connects to API Gateway, which uses consistent hashing on document.dot to route the WS connection to the correct document server responsible for that doc.
Benefits.
Load distribution. When servers join leave, only a small fraction of docs connections need remapping. Servers monitor Zookeeper for ring changes, initiate state transfers. Challenges.
State needs to move during scaling. Disconnecting users, moving document ops history. It's complex and painful to manage seamlessly. Maybe Layer 7 load balancer helps by querying Zookeeper for the right server based on doxed. WebSocket per user or per document.
Source implies OT needs connection, per document per user. If user opens many docs, many connections, maybe PubSub could allow 1 WS per user, fanning out doc updates. But OT's central server model points towards per doc connection. Okay. Second deep dive. How to handle document history and compaction, reducing the operations log. Problem. Storing every single operation. Log gets huge. Reconstructing docs becomes slow.
Approach 1, offline compaction service.
Yeah. Separate service loads all ops for a doc, compacts them, for example, merge inserts, writes compacted version to new document versioned, tells active document service to switch. Challenges. Moving active state is hard. Offline might miss latest edits.
So the great solution, approach 2.
Online snapshot compact operations, document service initiated. The document service does it itself when it has exclusive ownership, ideally when the document is idle, no connections.
Why idle?
Safest time, no active edits. All ops are already in memory. Flow, when last client disconnects. 1. Take in memory ops. 2. Offload to low priority process thread for compaction. 3. Write compacted ops to DB under new document version of it. 4. Flip document version in metadata DB. Benefits.
Safely compacts without coordination issues. Challenges, risk increasing latency if compaction hogs CPU. Mitigate with low priority. How do you reconstruct state then?
Store ops and document operations DB. Cassandra's good. When loading, fetch latest compacted state plus any later ops from the log. For super popular files that never go idle, server keeps in-memory state, gives that to new clients, compacts when ops threshold reached. Okay. Third deep dive. Consistency trade-offs and advanced topics. Staff plus level.
Key points. OT's statefulness. Document service must keep state for OT. No way around it. CRDTs versus OT. CRDTs better for more collaborators, P2P, offline, like Figma maybe. OT better for text, central server model.
Latency for global users. Place WS server geographically between users. OT CRDTs tolerate some latency if edits aren't simultaneous on same words. Awareness cursors helps users avoid collisions socially.
Other advanced ideas.
Durable objects maybe, but interviewer might not know it. OT itself handles transaction serialization. Event sourcing view.op is event stream. Maybe use Kafka plus Flink for compaction. Hashtag tag 8. Design a distributed cache.
All right, let's dive into a really foundational piece. Designing a distributed cache. We're talking key value storage across multiple machines, built for lightning fast access, super common, super critical performance layer.
Exactly. The challenge is hitting high throughput, maybe 100K request spec, managing potentially large data volumes, terabytes, while maintaining consistency, fault tolerance, and of course low latency across a whole network of machines. Implied NFRs, high availability, fault tolerance, scalability, 1 TB data, 100K RPS target, low latency.
That capacity target, 100,000 requests per second, managing 1 TB of data, that's way too much for one machine, right?
Absolutely. A single powerful node might store 1 TB, but it can't handle 100K RPS. If we replicate data, say 4 copies for availability and read scaling.
Each copy handles maybe 25K read sec.
Right. But every write has to update all 4 copies. Big challenge for write latency. Clearly needs a distributed multi-node design.
Okay. At its heart, what is it? Core entities.
Simple. The key value pair, the data itself, and internally, a node representing an entry in the cache's eviction structure, maybe holding the value in expiry time.
And the API. Looks simple.
Deceptively simple, yeah. Conceptually, det key, set key, value, delete, key, key.
Okay, high-level design. Start with the building block. A single node LRU cache. How does that work?
Using 2 key data structures for O1 performance. 1, a hash table for O1, lookup, get, and insert update, set, mapped key to the internal node. Right. 2, a doubly linked list. Tracks the least recently used LRU order.
Yeah.
2, a doubly linked list. Access get or add update. Set move that node to the front of the list. O1, front, most recent.
Oh.
2, a doubly linked list.
Yeah.
Cache full need eviction. Remove node for the tail of the list. Tail least recent.
What about expiration, TTL?
Each node stores an expiry timestamp. Get checks it, removes if expired. Cache miss. Also, a background cleanup process usually swoops away expired items.
Benefits of this single node design.
All core ops, get, set, eviction are O1, super fast. Performance doesn't degrade with size.
But again, single node won't meet our scale. How do we distribute this? Let's hit the deep dives. First, how to achieve high availability and fault tolerance. Replication.
Right. Replication is key.
Synchronous replication. Write comes in, primary updates locally, synchronously updates all replicas, waits for all acts, then response to client.
Damn sides.
High write latency, waiting for slowest replica. Lower availability, any slowdown replica blocks writes. Scales poorly with more replicas. Good for strong consistency, but often overkill for caches. Approach 2, good solution. Asynchronous replication, leader-follower, more common for caches. Primary accepts writes updates locally, responds to client immediately, then propagates changes to replicas asynchronously.
Benefits.
Better write performance, no waiting. Higher availability, writes proceed if replicas are down. Scales better. Fits caches where some temporary staleness on replicas is okay. Replicas might be briefly stale. Failure recovery, promoting new primary, ensuring replicas catch up, is more complex. Conflict resolution usually not needed as primary dictates order. Approach 3, more scalable. Peer-to-peer replication. All nodes are equal except reads writes. Changes spread via gossip protocols. Nodes talk to random peers.
Benefits.
Max scalability availability. No single point of failure. Writes process locally first, then async propagate.
Challenges.
More complex implementation. Might need conflict resolution if concurrent writes happen on different nodes, though consistent hashing usually directs writes for one key to one node. Quorum reads writes possible, but add complexity. Recommendation.
Async replication offers a good balance for caches. Peer-to-peer for max scale if eventual consistency is fine.
Okay.
Second deep dive, how to ensure scalability. Data distribution and handling those dreaded hotkeys. Problem. Single node can't handle 1 TB 100K RPS.
Solution. Consistent hashing, data partitioning. Distribute keys and requests intelligently across nodes. Clients or a router use consistent hashing to find the right node for a key.
Benefits of consistent hashing again.
When nodes join leave, only a small fraction of keys need remapping. Minimizes data movement during scaling. Needs a client library or query router, plus something like Zookeeper or client itself to hold the node mapping.
What about hotkeys? One key getting all the traffic.
Big problem. 2 scenarios. 1. Handling hotkeys. Read heavy. One popular item gets hammered with reads. Solution. Create multiple copies of the hotkey's value spread across different nodes. 4 copies. Each handles 25% of reads. Benefits. Spreads read load effectively. Challenges. Keeping copies in sync. Eventual consistency, usually okay. Overhead of monitoring hotkeys, managing copy lifecycle, best for read-dominant keys. 2. Handling hotkeys, write heavy. One key gets all the writes, example, a global counter. Solution. Key sharding with suffixes. Split counter.x into counter.x.1, counter.x.2, distributed across nodes. Writes randomly pick a shard suffix to update. Reads query all shards and aggregate your gsum. Benefits. Distributes write load for decomposable ops like counters. Challenges. Increased read complexity latency. Aggregate from many nodes. Needs careful shard count choice. Not for ops needing strict order atomicity across all updates. Another alternative for hot writes. Write batching. Group multiple writes, e.g. counter increments, into batches. Commit batch to cache storage. Reduces load, but trades delay for visibility. Eventual consistency okay for metric scanners.
Key takeaway.
Show you know hotkeys are a real operational pain and have strategies to mitigate them.
Okay. Third deep dive, how to ensure performance. Network and client optimizations. Problem. Distribution adds network overhead.
Solutions. Request pipelining. Client sends multiple requests to a server without waiting for each response. Improves throughput. Connection pooling. Clients maintain pool of open connections to cache nodes. Reduces connection setup cost. Data serialization. Use efficient formats, protobuf thrift to minimize network payload size. Client-side caching, L1 cache. Application keeps small local cache for hottest data. Avoids network trip entirely sometimes.
Anything else?
Durability. Mention using a write-ahead log, WAL, for writes alongside the in-memory map for recovery. Eviction policy. Note that changing LRU to LFU mostly affects low-level implementation, not the distributed concepts. #tag9, design a job scheduler.
All right, next up, let's look at automation. Designing a job scheduler. Think of it as the back-end's ultimate cron, a program that automatically runs tasks at specific times or intervals, essential for repetitive work.
Exactly. A job scheduler automates tasks like batch processes, maintenance scripts, data pipelines. It's critical for back-end ops, so the non-functional requirements are demanding. It needs high availability. Availability consistency here, better run twice than miss. Needs precision, execute jobs within 2 seconds of scheduled time, needs scalability, support up to 10,000 jobs per second, and guarantee at least once execution.
Whoa! 10,000 job sec within 2 seconds. That's a tight window. Capacity estimation reflects this. 10K job sec means huge database load if polling. If using SQS, it can handle 10K message sec, standard queues, but likely needs quota increase, maybe batching. Points to a distributed high-perf solution.
Right. Core entities.
The task definition.
Yep.
Jobid, usered, schedule, cron, expression, or timestamp.
A specific run instance, executioned, Jobid, schedule time, actual start time, status, pending, running, completed, failed, attempt. 3. Time bucket. Internal concept for partitioning. Unix timestamp rounded down exactly to nearest hour. Exact time 3600, 3600. Uses partition key for efficient querying.
EPI, more internal, right?
Yeah, mainly internal, implicitly. Create job API for user services to define jobs. Update execution status API for workers to report back.
Okay, high-level design, the obvious first thought.
Naive approach. Direct database polling. A watcher service constantly queries an executions table. Find jobs due in next 5 months. Database uses time bucket, partition key, and execution time sort key. Flow. Watcher queries DB, gets jobs, distributes to workers. Workers run. Bad idea.
Why bad?
Large queries. Hitting DB every 2 secs with potentially huge queries kills stability. Precision window, overhead, querying, distributing, makes hitting the 2-second target hard. Hot partitions. Using time bucket rounded to the hour. All jobs for that hour hit 1 partition. Peak time's a disaster. Even 5-minute polling hits the same partition key. Doesn't scale.
Okay, direct polling is out. The great solution.
2-layered scheduler architecture, durability plus precision. Phase 1, database query, durability layer watcher service. Watcher still queries executions table, but less frequently, maybe for jobs due in next 5 minutes. Ensures jobs are durably stored and picked up eventually. Phase 2, message queue for near-term scheduling. Precision layer message broker. Instead of direct distribution, Watcher pushes these near-term jobs into a message queue that supports delayed messages or scheduling. The queue delivers the job to workers just before the scheduled time.
Components.
Watcher service. Polls DB pushes to MQ. Needs to be distributed, leader follower, to avoid SPOF. Failure means potential delay. Message queue. Scheduler. Holds jobs, makes visible precisely when due. Worker service. Consumes from MQ, executes jobs. Much smarter. Okay, let's deep dive into the queue choice. Failure handling, idempotency. First deep dive. Choosing the right message queue for scheduling. Needs delay support, reliability, scale. Options. 1. Redis with sorted sets. Use these sets, score exec time, background process pulls Redis, moves due jobs to list queue. Benefits. Fast perf, subs M's latency. Challenges. High operational complexity. Custom logic for retries, failures, replication. Basically building scheduler yourself. Works maybe at moderate scale. 2. RabbitMQ plus delayed message exchange plugin. Publish with delay param. Robust broker, clustering for HA, benefits. Solid messaging features, challenges. Delay is plugin based, maybe less reliable at huge scale. Manual retry logic needed. Higher ops overhead than managed. Precision might not be perfect. 3. Amazon SQS with delivery delay. Great solution. Watcher sends message to SQS with delay seconds. SQS handles the rest. Benefits. Fully managed. AWS handles scaling, partitioning. Hits throughput needs, 10K sec with quota bump. Can use multiple queues for priority. Challenges, delay seconds capped, 15 minutes for standard. Watcher pull needs to be frequent enough, CG 5 minutes. Standard SQS isn't FIFO, ordering not guaranteed, but guarantees at least once delivery.
SQS seems pragmatic for cloud. Okay, second deep dive. Handling job failures. Visible errors versus invisible crashes.
For visible failures, errors in job code, exponential backoff and retries. Job fails, retry after increasing delay, 1s, 2s, 4s, limit retries, for example, 3 times. Still fails. Mark failed in DB, stop. SQS often handles backoff automatically for redelivery. Queue manages retry count, not worker.
What about invisible failures? Worker crashangs.
Yeah.
Harder to spot.
Approach 1. Health monitoring system. Workers expose GET health. Central service polls. Worker fails checks. Mark dead. Reassign jobs. Challenges. Latency and detection. Extra service needed.
So the great solution?
Leverage the message queue visibility timeout like SQS. 1. Worker consumes message. It becomes invisible for timeout period, 4G30s. 2. Worker finishes successfully. Deletes message. 3. Worker crashangs. Fails to delete before timeout. Message becomes visible again. Another worker picks it up. Benefits. Handles crashes automatically. No external health checks needed. Difference. Visibility timeout detects worker crashes. Exponential backoff handles visible task errors. Complementary.
Critical third deep dive. Ensuring idempotency. At least once means jobs might run multiple times. How to prevent duplicate effects. Money transfer, email sent.
Right. Naive approach. Just run it every time. Bad idea.
Yep.
Leads to data corruption.
The great solution.
Design jobs to be naturally idempotent. The job logic itself ensures running multiple times has same effect as once. Use idempotency keys and conditional operations. Instead of increment counter, job is set counter to X, using maybe compare and swap or version check. Instead of send welcome email, job first checks welcome mail flag. If set, do nothing. Each execution carries unique ID. Downstream services can use it to dedupe results. Benefits, most robust. Offloads to task implementation, example, email. If email sent but flag update fails before commit, Retry sends email again. If getting email twice is okay, fine. If not, critical data needs proper transactions.
Okay, fourth deep dive. Database and data model considerations, that executions table.
Right, time bucket, hourly, as partition key plus execution time as sort key can cause hot partitions. Millions of jobs in 1 hour hit one partition. Mitigation, more granular time bucket, or compound partition key, time bucket sharded, shard ID random, or from job ID to spread load.
Querying jobs versus executions.
Job ownership, query jobs table, index partitioned by user ID to see jobs a user owns. Status history, query executions table, needs GSI on user ID for efficient lookup of a user's history.
RDBMS versus NoSQL.
RDBMS, PostgreSQL, fine for jobs. For executions, 10K write a sec. NoSQL, like DynamoDB, scales better for writes, but needs GSIs for queries.
Recurring jobs.
Recurring jobs. Don't scan jobs table constantly. Have separate forward-looking cron job create executions entries for recurring jobs for next few days. Efficient.
How do multiple workers avoid picking up the same job?
SQLDB. Select. For update limit 1, row lock. SQS. Visibility timeout handles it automatically. Watchers. If scaled horizontally, partition the DB query space. Each watcher queries specific partitions.
Fifth dive. Workflow orchestrators, like Airflow.
For DAG workflows pipelines, chain tasks with dependencies. Different problem than simple job scheduler. Deeper topic, may be out of scope unless asked.
Sixth dive. Worker configuration and deployment.
Allow users to define worker type, container size, SML/XL, and base image, runtime NV. Deployment. ECS often better than Lambda for steady workload. Cheaper. Lambda cold starts can take seconds, breaking twos requirement unless using provisioned concurrency. Hashtag tag 10. Design a payment system.
Okay, our final deep dive today, and it's a huge one. Designing a secure payment processing system, handling financial transactions. Integrity, reliability, security are absolutely non-negotiable. This is the core of e-commerce.
Absolutely critical. Transaction safety, durability, high throughput paramount. You're dealing with asynchronous external payment networks, need immutable audit trails. The non-functional requirements are intense. Strong consistency for payment states. No ambiguity. Durability of all payment records. Never lose data. Scalability. Handle 10,000 plus transactions per second, TPS. Scalability. Transaction safety and financial integrity, even with flaky external networks.
10,000 TPS with strong consistency. Yeah, that's where the real challenge lies. Capacity estimation. 10K TPS. If using Kafka, needs multiple partitions, 3 to 5 maybe, just for throughput. Data growth. 500 bytes a row, 10K TPS, equal 5 MB sec. That's 500 GB day, 180 TB year. Needs serious retention archiving planning.
Right, core entities.
Represents merchant's intent to collect payment. Payment intended, merchant intended, amount, currency status, created, processing succeeded, failed. Tracks the whole flow.
A specific operation, auth, capture, refund, linked to a payment intent.
Customer card details, etc. Merchant API keys, callback URLs.
API interfaces.
Create payment intent. POS payment intents, major returns payment intent. Process payment. This is special. Client-side interaction direct with our payment service avoids merchant server touching sensitive data. Get payment intent status. Get payment intent stop. Payment intent returns payment intent. Initially polling webhooks later. Okay, high-level design. Security and safety first.
Merchants create payment intent. Flow. Merchant server API gateway payment service. Payment service validates, creates payment intent record in a transactional, highly available DB like PostgreSQL for strong consistency.
Requirement 2. Customers pay with card. Security is everything here. Principle. Sensitive card data never touches merchant servers. PCI DSS.
Right, so approaches. Naive, client next source, merchant server, access, bad idea. Customer enters card on merchant site, merchant sends to us. Bad. Merchant is attack target, huge liability, even encrypted card data passing through merchant server, Ixul PCI scope help. Better. Client type frame math's getting warmer. Merchant embeds iframe from our domain. Customer enters card in iframe, data goes direct from iframe, our domain, to us via HTTPS, bypasses merchant, much safer. Challenges. iframe security depends on browser, limited customization, mobile usability issues sometimes. Card data unencrypted in browser before HTTPS transmit, though within our secure iframe. Great solution. Client-side encryption with JS SDK NACU. Best approach. Great solution. Client-side encryption with JS SDK NextUS. 1. We manage encryption key pairs, public-private. Great solution. Client-side encryptions with JS SDK -US US2. Merchant uses our JS SDK with our public key. Great solution. Client-side encryption with JS SDK match US. 3. Client encrypts card details in browser using SDK. Great solution. Client-side encryption with JS SDK -ESE. 4. Encrypted blobs sent to our payment service. Raw card data never leaves client unencrypted, never touches merchant server. Great solution. Client-side encryption with JS SDK DUSS. 5, we decrypt with our private key. Benefits, most secure. Keeps merchant clearly out of PCI scope for card data handling. Okay, once we securely get card data, payment processing, payment service validates, interacts securely with external payment gateway network, Visa, MasterCard, Stripe, etc. Updates payment intent status, processing succeeded, failed, based on network response.
And requirement 3, merchant's view status. Initial approach. Polling. Merchant calls GT payment intents. Dot payment intended repeatedly. Challenges. Not real time. Creates load. We'll fix with webhooks later.
Okay, basic flow established. But the deep complexities. Immutable records, handling external async failures, real-time updates for merchants. Let's dive in. First deep dive. How to ensure durability and immutability of payment records. Auditability. Problem: simple updates overwrite history. Bad for audits, disputes.
Naive approach. Backups plus logs.
Insufficient. Allows point-in-time recovery but loses granular history needed for audit.
Better. Separate audit tables.
Better approach. Separate audit tables. Append only log. Maintain payment audit log. Every state change triggers insert to audit log within the same transaction as main table update. Begin, update payments. Insert audit log, challenges. Relies on app code, always remembering to write audit record, error prone. Increases transaction complexity latency.
So the great solution.
Change data capture CDC with event source in Kafka. Decouples operational DB from immutable audit trail. Architecture. Operational DB, current state, high TPS, .cdc, Debezium, Kafka, immutable event stream. Facilitators, audit analytics, webhooks. Kafka events. Captures DB, insert, update, delete as events. Benefits, immutability. Kafka stream is append only, verifiable. Perfect audit trail. Decoupling. DB handles key tasks. Kafka consumers handle audit analytics without contention. Durability. Kafka replicates events 3x typical. Retains short-term 730 days, then archive to object storage S3 permanently, every change flushed to S3 forever. Reliability. CDC works at DB level, captures all committed changes, no reliance on app code, independent scaling. DB, Kafka, consumers scale independently. Challenges. CDC itself can be SPOF, mitigate with multiple instances, monitoring. Kafka partitioning, partitioned by payment intended. Ensures all events for one payment are processed in order. Critical for consistency.
Wow, CDC plus Kafka is powerful for this. Okay, second deep dive. How to guarantee transaction safety and financial integrity despite asynchronous external payment networks. Problem. External networks are async. Timeout might happen, but transaction succeeded externally. Marking failed prematurely is wrong.
Right. Naive approach, manual reconciliation, timeout, mark payment pending verification, finance team manually checks later, use idempotency keys, merchant ID plus unique key as DB constraint, merchants retry with same key, get existing record, challenges huge manual burden, treats reconciliation as exception, not core process, DB hit with operational plus reconciliation queries, bad.
The great solution.
Asynchronous, event-driven reconciliation with idempotency. Embrace the async nature. Leverage CDC stream. All status changes, internal or from external network webhooks, flow into Kafka. Reconciliation service. Consumes Kafka stream. Continuously cross-references internal state with external network reports, daily files, APIs. Automatically resolves pending verification states. Idempotency keys, detailed, crucial. Unique client string per request. Payment system uses it to dedupe. Check on POST payment intents. If key exists, return existing record. If not, create new. Distinct from nonce, which is more for autoplay prevention. Benefits. Automated reconciliation. System designed for async reality.
Okay. Third deep dive. How to provide real-time status updates to merchants. Polling is inefficient.
Great solution. Webhooks. Push-based notifications. We notify merchants proactively. Mechanism. Merchants provide callback URL plus subscribed events, payment.succeeded, etc. Webhook service. Consumes Kafka event stream. Sees subscribed event. Construct webhook payload. POST's payload to merchant's callback URL. Example payload. JSON with event type and data. Payment ID, amount, status, etc. Benefits. Real-time updates for merchants. Trigger fulfillment. Reduces our polling load. Webhook system challenges if designing it fully. Exactly. Once delivery hard, backlog handling, versioning, rate limiting.
Final deep dive. Server and database scaling.
Service. Stateless. Payment service, webhook service, reconciliation service, all stateless, scale horizontally behind LBs. Standard. Kafka cluster, needs multiple partitions, 35 plus, and brokers for 10K TPS. Partitioned by payment intended for ordered processing.
Database, operational DB projections.
Needs to handle 10K TPS writes for current state. Data growth, 180 T by year. Needs retention archiving plan. Move old data 3 to 6 months to S3 GCS via jobs. TPS calculation note. Source mentions 10K TPS overall, but maybe 1K writesec to DB. Could be batching or internal details, but DB needs to handle significant write load, maybe similar to Kafka MSG rate if 1.1 mapping.
Transactionality.
Ensured by DB write first, then CDC to Kafka. DB write fails, no event. DB write succeeds, event guaranteed eventually via CDC Kafka reliability.
Wow, okay. We've just covered a monumental amount of ground today, truly diving deep into 10 distinct and incredibly complex system designs, from Google Docs collaboration to job scheduler precision and the critical integrity of payments. What a journey.
It really has been. We've seen how these common architectural patterns, message queues, consistent hashing, careful replication, they form the bedrock for such vastly different applications, haven't they?
Absolutely.
And how those fundamental choices about consistency, durability, handling scale, they can truly make or break a system.
It's amazing how these core concepts just keep recurring, providing elegant solutions across all these complex domains. And those deep dives handling hotkeys, ensuring idempotency, mastering fan-out strategies, they really highlight the nuances that take a system from just working to being truly resilient and performant.
Yeah, the journey through these designs, it reminds us that while the problems might seem unique on the surface, news feeds versus auctions versus payments, the underlying principles of good system design are pretty universal. It's always about understanding the trade-offs, anticipating failures, and constantly asking, what does this mean for the user and how can we build it reliably?
Exactly. And that, my friends, is what it means to truly dive deep. Keep exploring, keep learning, and keep building. Until next time, stay curious.